Welcome to the second half of the morning session. I am the voice of Christian Kratenthaler. So do not think that you can get away with anything just because it's me. He's sitting in the front. He sees everything. I'm very pleased to introduce Shashank Kanade, who will be talking on the A2 Andrews-Schilling-Warnaar identities.
Thank you.
よろしくお願いします。
ありがとうございます。Okay, so this is a joint work with Matthew Russell, and I should thank Ola Warner, who gave generous insights throughout this project. Okay, so this talk, So this talk lives in the universe of Rogers-Ramanujan type identities, which are Q-series identities of this general shape, where you have a Q hypergeometric sum, Q raised to a quadratic form divided by Pochhammer's. I've written down the notations on the board for your quick reference, equals an infinite periodic product, and in this case it is periodic modulo 5. And Rogers-Ramanujan identities themselves are a pair of identities. These are very similar looking identities, and they were discovered more than 100 years ago. By Rogers, Ramanujan, and Schur. But anyway, there are combinatorial interpretations of these identities, which at the moment I'm not going to worry so much about. And it's important for me that these are related to various algebraic structures like VOAs, affine Lie algebras, and so on. In particular, these two identities are related to SL2 hat. And in some sense, we understood SL2 hat more than 4 decades ago. And we are just beginning to understand SL3, which is what this talk is about. At the end, I'll mention some connections to knot theory as well. Okay, so this is about identities of this same shape, sum equal to product, for SL3 hat now. And now it's Andrews-Schilling-Warnaar's work from 1999, where the products came from what are called principal characters for standard modules for SL3 hat. Standard means it's integrable and highest weight. So ASW gave the sums, corresponding sums, and the mechanism by which they proved that these are equal is what they invented at the time. It's called the A2 Bailey machinery. For us, we are going to take a slightly different route. We are going to soup up these sums with a new statistic Z. Conjecturally, then the sums will be related to cylindric partitions. And then if you set Z equal to 1, then you have properties of cylindric partitions which give you the required products. So please remember that we're going to take this route and not this route. Okay? So really our results, our conjectures are going to live in the bivariate world of ZQ generating functions. Okay, so what are these principal characters? So I'll stick to SL3 hat, but a lot of this slide is much more general. So let's take a dominant integral weight for SL3 hat. So it's got 3 labels, C0, C1, C2, which will be non-negative integers. So this is going to be the highest weight of an integrable highest weight module for me. And there is an associated level of this module. So it's just the addition of these 3 labels. And I'll denote it by L for level. And ultimately, you're going to get sum equal to product identities in which the modulus on the product side, so the periodicity in the product, would be the level plus 3, that's M, and 3 is really the dual Coxeter number for SL3 hat, so that's where that 3 is coming from. Anyway, at the moment, it's not so important. It'll come up later, though. Okay, so first let me tell you what is a principally specialized character. So take the full character of your module with that highest weight lambda, ignore the highest weight, and now all the formal variables that you have, the formal exponentials corresponding to every node in your Dynkin diagram, you set all of them to Q. Okay? That's what a principally specialized character is, but I'll need a further normalization of this character, which I'll call principal character. And what I'm going to do is I'm going to divide out by the principally specialized character of level 1 module. It doesn't matter which level 1 module you pick, they will all give rise to the same principally specialized character. So this is a well-defined object. Okay, is that clear? So first you principally specialize and then you normalize as well. And you will see that there are nice character formulas, Lepowski's numerator formula, Wildcat's character formula, by which this is straightforward product. And you see it's periodic modulo M. And you also see, because of every node being set to Q, you will see that this here exhibits the full Dynkin symmetry. So C0, C1, C2, they appear in a totally symmetric way in this case. Okay?
I'm sorry, could you say again what is capital L?
Capital L. L is the irreducible highest weight module with lambda as the highest weight. Okay? All right, any other questions? Okay, so a certain arrangement of modules, for me to tell you what these identities are, a certain arrangement is going to be important. So let's take a big enough level, level 11. So remember, our characters are going to be going to exhibit full Dynkin symmetry. So I could just assume that the labels are in weakly decreasing order. So here are all the possible highest weights. And what I'll do is I'll put them, the row will be the second number, so 0th row, first row, second row, third row, fourth row. And the column will be given by the last entry, so 0th column, first column, and so on. And if you arrange them in this way, you'll see that you get a triangular arrangement, and at some point this triangle starts receding. So I'll draw a line, and this line is very important. I'll draw a line where this triangle starts receding. And it turned out that in 1999, in Journal of AMS, ASW found out identities corresponding to this diagonal and a couple of modules that lie here. Okay? So they found out Rogers-Ramanujan type identities corresponding to principal characters of these modules. Okay, so please remember this line, it's very important. All right. So here are the sample identities. So this is an identity. It's easiest to start with levels that are 3K plus 1. So this is an identity. So you see a sum, and the quadratic form here is coming from Cartan matrix of A2. There is some linear deformation in the exponent of Q that depends on exactly which module you're looking at. And you see that there is this sum, and you see that it's equal to up to a pesky factor of 1 over Q infinity, the principal character of this module. This is at the apex of the triangle, 7, 0, 0. Okay? And that's this infinite product. This factor bothers a few people in the audience, but it doesn't scare me. I'm looking at Ola here, but anyway. All right, so very similar if you go level 5, so 3K minus 1, it's just that this last quadratic form changes, but roughly the shape is the same, and that's good. And levels that share a factor with dual Coxeter number are funny, and you'll see that the ligand corresponding to the very last pair of variables in your sum is a little different, but overall it's still the same shape. And then if you increase your levels, next block would be levels 8, 9, 10, you'll see bigger and bigger sums coming up. Fine? So they discovered some identities, but not all, and that's what we did. That's the point. I mean, conjecturally. So that's the main question. They discovered some, not all, identities, and can we finish it? All right. So let me switch gears for a bit. Let me talk about cylindric partitions, because remember, we are going to go in that ZQ world. Okay, so a plane partition is just you take a diagram of a partition and you fill it up with numbers which are weakly decreasing along rows and columns. And if you think of the numbers in the boxes as heights, then you get a three-dimensional shape. And I might have stolen some code from Jiangsu Kim that's available on somewhere to draw this nice picture. So thank you. All right, and what is a cylindric partition? Cylindric partition is going to be some sort of a truncation and a repetition of this shape. Okay, so I'll tell you now what that is. For us, cylindric partitions come with a profile, which is a sequence of non-negative integers. For us, we will have 3 non-negative integers because it's SL3. Okay, so for example, 3, 1, 2. So if you fix this profile, it's going to be ultimately related to the principal character of this module. Okay, and what is a cylindric partition? Well, if you have 3 entries in your profile, then it will be really a partition with 3 rows in it. It's a skew partition, plane partition. I'll tell you what this 4th row is. That's just copied from the bottom one. Okay, but it's not officially a part of your cylindric partition. And the profile comes up in the skewness of these rows. So this 3 is this is 3, that's 1, and that's 2. And the point is, even after you copy this bottom row on top with this skewness, then the weakly decreasing property should be preserved. Okay? So that's what a cylindric partition is, and it's called cylindric because of this repeating pattern. Okay, so the total skewness, 3 plus 1 plus 2, that's going to be your level. The weight of this cylindric partition is the addition of all the numbers, and the maximum part, which will be corresponding to Z, is 7 here. Excellent. Okay, so let's take a profile. Let's take the class of cylindric partitions with that profile, and you form a bivariate generating function called f. But this is not what's going to be important for, I mean, this is important, but for us, a certain further modification is what is really related to the ASW identities. So we'll need to modify this with a few poke hammers. So it's the h function that is related to ASW identities, as it turns out. It's a certain deformation of these. Okay, so remember, it's not straight up generating function, but some modification of these. Okay, good. So there are 3 key points you should remember. By the way, so if you set z equal to 1, then of course these two factors drop out. So at z equal to 1, this is equal to that. So that's my first key point, that it's equal to that. And after setting z equal to 1, you just get that principal character. In this case, okay, I've written it more generally. This is for SLR plus 1 hat. For us, take r equal to 2. Secondly, if you keep the z in there, then there is a nice cyclic symmetry of this thing where, I mean, because of this repeating condition, it doesn't matter which one you call as the bottom row. So that means that there is a cyclic symmetry. But further, if you set z equal to 1, then you're going to exhibit the full Dynkin symmetry. So you're going to also have a reflection there because of the relation to this character. And the third important part is that if you fix your rank, so SL3 hat, and you fix your level, then the totality of the h functions that you have, they are unique solutions to a Cortiel-Welch system of ZQ difference equations. So in other words, completing this ASW identities, you could say, is solving, give me a solution to the system of Cortiel-Welch equations. But I don't like to put it that way because it's not like we have a solver where you give us a difference equation and we solve it. It's not that. It's just that ultimately we do end up solving it. But that's a rephrasing of what the problem is. Excellent. Okay, so now remember, I'm going to be in the bivariate world, so I only have the cyclic symmetry. So for example, 1010 is different from 1001. Okay, so I'll enhance this diagram with everything that's possible. And now let me tell you what our result is. I will not be able to tell you in precise terms exactly what it is because it's a bit complicated, but I'll give you a feeling for what it is. Right, so here are our conjectures and results and so on. So the first is, for every level and above that line that I drew, remember there was a line where the triangle receded. So for all the compositions that lie above the line, in this SL3 hat case, we give explicit conjectural ZQ Andrews-Schilling-Warnaar style sums for these bivariate H functions. Okay? So that's our main conjecture for everything above the line. Secondly, what happens below the line? Well, it turns out Cortiel-Welch system of equations, once you know what happens above the line, it completely determines what happens below the line. It's just that we don't have explicit formulas. Okay, so that's good. I mean, it's not good really, but we did what we can. All right. And now, if you prove these conjectures, then remember, after proving these conjectures, if you set z equal to 1, you're going to get sum equal to product identities by the properties of cylindric partitions. Okay? But our conjectures are really saying much more. Excellent. So let me show you how, for example, in level 7 this looks like. So you remember this shape, and what it ends up being, okay, so first the z corresponds to just very easy, z to the r1. R1 is the biggest of the r's. And all that it corresponds to, completing these identities, corresponds to figuring out what function to plug in every summand. Okay, so here's how it looks like. So this is your triangle that you know. And above the line, if your entries are in order, then this is how it looks like. It's very simple actually. There is a nice pattern. For example, if you go 700, it's this, and you move one line down to 610, you're striking off one of the r's. If you move one line down, you're striking off another of these r's. So there is a nice pattern here, and it generalizes to higher levels. And as you move to the right, then there is something happening. It never gets any worse than these these formulas here, that's the pattern. If you're still above the line, but now your, I don't know, compositions are out of order, then again, you have some formulas, they nicely generalize. But really, below the line, things really get ugly. Okay, so these formulas are becoming more complicated, and there is one more here, and as the level grows, there is really no nice pattern below the line. But it's fine. I mean, once you know what happens above the line, everything below the line is determined. Okay, so that's our conjecture for every level. Okay, so did we prove anything? So it turns out, okay, we were able to prove something. So when the level is 2, 3, 4, 5, 7, we explicitly proved our conjectures. So you see that there is plenty of room to play, infinitely many more remain, if anyone wants to try. And 3 and 7 are in red because these were brand new at the time. So last year, these were brand new. Okay, how did we prove it? Well, we just want to show that our functions satisfy the Cortile-Well system of equations, and we did it using computers. Okay? So in particular, we still don't know exactly why these sums count the cylindric partition. We don't have a bijective proof. We don't have any reason why these sums actually count the cylindric partition. We are essentially proving the uniqueness of the generating functions, right? We are using the uniqueness. So it's computer proof. So again, I mean, there is quite a bit to be done here. And you will see that this level 6 is conspicuously missing, and that is still unproved. And the reason is that levels that are divisible or levels that really share a factor with the dual Coxeter number are somehow funny. So anyway, so that's still open. Okay, what's more? So recently, so remember I said, if you first prove our ZQ conjectures, then set Z equal to 1, you're going to get sum equal to product identities, right? But you could just short circuit all that, and you could ask, can you prove the sum equal to product identities? So recently, a few months ago, Ola has really finished the A2 Bailey tree that was started in his 1999 paper. And it's a very different mechanism than the cylindric partitionist business, but he is able to prove all the sum equal to product identities that lie above the line. Okay? And of course, he's not saying anything for what happens below the line because we don't have explicit formulas for what happens below the line. So again, he has done everything that can be done, in a sense. So this is very recent, a few months ago. But I should emphasize that our bivariate conjectures are still open. Okay? And the smallest unproved level is 6. All right. Now for something completely different. So it turns out that a very big class of knots, including alternating knots, have this very curious property with regards to SL2 colored invariance. So what you do is you take your knot and you color it with n-dimensional irreducible representation of SL2, and you get a corresponding invariant. Okay? And so for every n, you're going to get an invariant, so you'll get a sequence of Laurent polynomials. Now, what happens is that these polynomials, they start at a different location, so their lowest degree term is going to be different. So what you do is just for every one, divide each of those invariants by their trailing monomial so that they all start as 1 plus 1 plus 1 plus ... And turns out for a large class of knots and links, this has a stable limit, which is often a very interesting Q series, like a theta function, false theta function, and so on. So I'm just going to play the same game, but with SLR invariants, and in this case, SL3 invariants. So let's take the torus knot 3p. Okay, so you take 3 strands, you twist them p times, and then you connect them up. Okay, and I'm going to color this knot. So okay, so for me to get a knot, I have to say that 3 and p are co-prime. Remember that thing about levels divisible by 3 being funny? That's again coming up here. So assume that 3 and p are co-prime and color it with this module of SL3. So with the highest weight n lambda 1. Okay? And you'll get a corresponding invariant.
Sorry, what is
N
n?
is just a non-negative integer, n lambda 1. So the symmetric power of the defining representation. Good. So I have a sequence of invariants again. And turns out this again has a limit. So you fix your knot, but now you just take this n going to infinity. Okay? And again you do this shifting procedure, and you will see that up to some factor, which doesn't really depend on the knot, it really depends only on the Lie algebra. You see the denominator of SL3 coming up. You're getting the principal character of the module that lies at the apex of that triangle. And it's really in the product form that you get this here. Okay? It's not the sum you get, it's the product form of that character you end up getting. This is a tiny slice of a much more general theorem that I have, which is about principal W algebras of type AR. You heard that name in Inoue San's talk, principal W algebras. Anyway, so this is a small slice of that theorem. And then the question is, can you do some other calculations of these invariants to illuminate where the sums are coming from or where the cylindric partitions are coming from? So remember I said that what you're getting are products. What about the sums? Can you do some other not theoretic business to get the sums? Okay, so that is my talk, but it looks like in the interest of time I was not able to talk about the work of Omar Fora, Sylvie Cortil, Jehan Doos, Ali Unju, Walter Bridges, Shunsuke Tsuchioka, and Trevor Welch. So I apologize to all of these people who have written very beautiful papers in the last few years about all of this stuff, but that's it. Thank you.
Any questions or further apologies? Ben.
Can you say something about what these recurrences look like that you're using in your proofs?
Repeat the question.
The question is, can I say something about what these recurrences look like? I can. It might be best if I just show you a picture after the talk. Yeah, it's really just a composition it's related to the 6 or 7 neighboring compositions that you get. And there is a nice rule to go from a composition to the neighboring compositions. And it's roughly the same as tensoring with a certain module.
Are they like linear recurrence or quadratic?
I mean, these are ZQ difference equations, so it's not exactly linear. Or, I mean, I don't know how to. Yeah, sure, yeah.
Krathenthaler thinks it's linear.
Yeah, yeah.
Other questions? Yes, in the back.
Can you say something about 2p Torres knot? I guess maybe that would be simpler.
Yeah, so if you look at 2p, the question is, can I say something about 2p torus knots? If you look at the SL2 invariants for 2p torus knots, you get the Virasoro 2p characters. And even if you look at SL3 invariants, you still get the same Virasoro characters. But you have to color it with that particular module that I was talking about, n lambda 1. Yeah.
So it says about reproducibility is funny. So is the funny somehow related to the fact that we have patients and then it would be relate that to the kids?
Sorry, I didn't catch the question.
So you said that like when you have divisible, when you're divisible by 3, something funny happens. And is it related? I guess I can assume it's related to the fact that you have all this base.
Oh, yeah. So if P and 3 share a factor, you don't get a knot, you get a link with multiple components. So it's the GCD of those two numbers, you get that many components, I think. I'm not a topologist, but that's what happened. And then when you get more components, then you get a very different kind of limit. Yeah, so yeah, so in this case, you're getting, the question is what limit do you get in that case, right? So in this case, I was essentially getting principal characters, and these are essentially modular invariant Q series. They are symmetric, but in that case, when 3 and P are, something like 3, 6, 3, 9, you get false theta functions as limits.
Yeah. Hugh.
This may be a very over-ambitious question, but so these cylindric partitions you can think of as having to do with a full heap of type, some type A full heap, and you could ask about other Dickin types, and do those things also show up, or is that sort of for the next 100 years or so?
So the question is, these cylindric partitions can be thought of as full heaps in type A. I don't know exactly what that is, but I would absolutely love to know what happens in other types. That's the first question I asked Christian when I saw him at this conference, and Ola, and
that's
don't
what the
think anyone
stickers are
knows.
all about.
Sorry?
That's what the stickers
Yeah,
are all about. Yeah.
That's what the stickers are, yeah. I would love to know what the analog is.
Okay, maybe one last question.
So when Jones computes the polynomial of the torus knots, he does have a sum, and it's a sum over irreducible characters. I'm wondering if you, of heck algorithms or something, so I'm wondering if you looked at all.
Yeah. So the question is, when Jones calculates it, he does it in a certain way, and have I looked at it? Yes. So the torus knots, there is a nice formula by Rosso and Jones to calculate the invariant, and that's exactly what I'm using. So yes.
Okay, in the interest of time, maybe.
Sorry.
Oh, go ahead.
But it's the sum side that's maybe interesting.
Oh, sum side. I don't know if they get the sum, but we could talk about it, yeah.
Yeah, so maybe we'll put off the other questions until lunch period. Remember that your lunch period is a little bit shorter than usual because there's a software demonstration at 1:45 today. But let's thank the speaker again.